A warm and hearty greeting is extended to all of you who have tuned in today to talk about our final lesson of this unit on variation. And I think you'll probably, hopefully, remember that most of you have studied variation in the past. We have direct and inverse variation that we're going to look at, along with a little bit of joint variation as we go here. So let's just remind ourselves of a few things. If we see the words y varies directly as x, y, when you see the word varies, you're always writing an equal k, and then since it's directly as x, we're multiplying. If it's y varying inversely or inversely proportional, we can divide by, and we want to divide by x here. In general, graphs of variables related by direct variation resemble graphs of power functions. With direct variation, as one variable increases, so does another variable. Examples of this: the amount of gas needed, and so the amount of money you must pay. Amount of money paid to fill the tank. That's an example of direct variation. The number of tickets you buy to a concert or a performance sporting event is directly proportional to the amount of money that you're going to have to pay. Graphs of variables related by inverse variation resemble graphs of power functions of the form y equal x to the n, where n is less than 0. And in this case, as one variable increases, the other variable decreases. For instance, if we think about the UV rating in the sun and the time it takes for a sunburn. As your UV rating goes up, the time it takes for a sunburn goes down. And so there are all sorts of examples of direct and inverse variation, and certainly we may have a discussion on those in class if you want. Be thinking about different examples that you may be familiar with. So guidelines for solving variation problems: you're going to write a general formula involving the variables and a constant of variation or proportion, that's k. We need to find the value of k. One of the things that this particular text and set of problems is good at, it asks for the value of k. Alright, so it gives you no choice. You've got to find the value of k, and then once you get the value of k, you can use that information to solve the next part of the problem, if there is one. So here in our first few examples, we're just asked to find, first to express a statement as a formula involving the given variables and a constant of proportion, and then determine the value of k from the given conditions. We look at this first one here. It says s, so I'm writing s, varies, there's my equal k, directly as t, so I'm multiplying by t. T is 10, k we don't know, s is 18, we're going to solve for k. This is 18 over 10, and folks, we always want to reduce. This becomes 9 over 5. There's my value of k. Our next example here, y. I write y is directly, so there's my equal k, proportional to x, and inversely proportional to the square of z, so z squared. If x is 4, z is 3, y is 16. So we've got 16 equal 4k over 9, and then we see that k equals 16 times 9 over 4. 16 divided by 4 is 4, times 9 is 36. There's my value of k. In our next example, y is directly proportional, so there's my equal k to the square of x, so there's x squared, and inversely proportional to the square root of z. If x is 5, z is 16, y is 10, so we've got 10 equal 25k over 4, 40 equal 25k K equals 40 over 25, which is 8 over 5. K is 8 over 5. So if you have questions on any of those, certainly bring those into class. You can see the problems for the class discussion and the homework listed there. So let's go ahead and jump in here to our next example. It says the intensity of illumination I from a light source. So let me write down, part A wants me to express I in terms of D and the constant of variation K. So the illumination I from the light source varies, so I need my equal K inversely as the square of the distance D from the source. So there's part A. A searchlight has an intensity of 1,000,000 candle power at a distance of 50 feet. Alright, so part B here, 1,000,000 candle power at a distance of 50 feet. So my K value here, when I multiply 50 squared by 1,000,000, let me just show that, 50 squared by 1,000,000, my K value turns out to be 2.5 times 10 to the 9. 2.5 times 10 to the 9. And maybe, let me write that here where it's a little clearer to read. 2.5 times 10 to the 9. Alright, now C wants us to sketch a graph of the relationship between I and D for D values greater than 0. Well, guys, we're just going to go for a fairly rough sketch here. Alright, we know that 50, and here's 1,000,000. Alright, and then 100. You guys can do this work. 250,000. Real rough sketch. This is what I'll be looking for in your homework as well. And then finally part D says approximate the intensity of the searchlight in part B for a distance of 1 mile. So D, part D, I'm looking for the intensity. My K value is 2.5 times 10 to the 9 over a distance in 1 mile. There's 5,280 feet. We're going to square that, and that comes out to be approximately 89.7, and that unit, the units there is, or are candle power, are the units that we're using in that particular example. So certainly if you have questions there, bring those to my attention. Let's slide on down here and take a look at our next example. It is known from physics that the range R of a projectile, so the range R of a projectile is directly proportional, equal K, to the square of the velocity V. So there's my equation. Now for part B, it says a motorcycle daredevil has made a jump of 150 feet. If the speed coming off the ramp was 70 miles per hour, find the value of K in part A. Well, so we've got R 150 equal K times my rate. That's 70 squared. So 150 equals 4,900 K. K equals 150 over 4,900, which will reduce to 3 over 98. And so now we look at part C. It says if the daredevil can reach a speed of 80 miles an hour coming off the ramp and maintain proper balance, estimate the possible length of the jump. So R is what we're looking for. We know that K is 3 over 98, and we are going to divide this, pardon me, we're not going to divide anything. We are going to multiply by 80 miles per hour squared. And this gives me a range of 195.9 feet. Alright, so if you have questions there, certainly bring those to our attention when we get to this in class. And our final example to look at for this particular unit deals with the ideal gas law. It states that the volume V that a gas occupies is directly proportional to the product of the number N of moles of gas and the temperature in kelvins, and is inversely proportional to the pressure. A says express V in terms of NTP and a constant of proportionality. So one more time, let me just go over this. The ideal gas law states the volume V that a gas occupies is directly proportional, so there's my equal K, to the number of moles of gas and the temperature T, and inversely proportional to the pressure P. So we've expressed V in terms of NT and P, and now we want to know what happens when, what is the effect on the volume if the number of moles gets doubled and both the temperature and the pressure are reduced by a factor of a half. So 1/2 the temperature and 1/2 on the pressure. Well, we simplify this expression. Notice how my 1/2s are going to drop, and what are we left with? We're left with 2 KNT over P, or this is twice what it was before. So if the number of moles is doubled and the temperature and pressure are both cut in half, your volume is doubled. Alright, so certainly if you have questions, please bring those to my attention. You can see the remaining class discussion questions we have and the homework we're looking at, and I'll look forward to talking with you about this in class.